Cryptocurrency has become really big lately, and we all know that it has something to do with cryptography, but it's kind of surprising how deeply I've gotten into cryptocurrency without really understanding all the cryptography behind it. So I've been trying to, in the last few months, kind of catch up and understand how the historical techniques that people have used for cryptography, how they relate to cryptocurrency. And so, I'm going to give a broad overview today of all the different cryptography techniques that are used in Ethereum and Bitcoin, and going over the algorithms and giving some conceptual overview of how all these different parts fit together. So what I'm going to talk about is kind of broken into three sections. So the first section we're going to talk about is classical techniques. So these are algorithms that were developed before the mid-1970s, and that's kind of the point where things changed. When we think of classical techniques for cryptography, mainly what we're thinking about is private key cryptography. So that's where you and the person you want to send a message to both know about some kind of secret key, and what you're going to do is you're going to take the message you want to send the person, you're going to encrypt that message with the key, and then send it over a wire to the other person, and then they can decrypt it with the same key. So this kind of cryptography is symmetrical. So you use the same key to encrypt it and to decrypt it. And so these concepts have been around forever. So if you look at like Julius Caesar and the Romans, they would use these kinds of encryption codes to encrypt messages between their different military units. But they didn't really back then have any conception for how to create any sort of truly secure type of cryptography. And the first breakthrough in classical cryptography came essentially around 1880 with something called the one-time pad. So this was sort of the very first secure way of doing cryptography, and most people here are probably familiar with it. And what's strange about it is that it's really still the most secure one that anyone has ever come up with. So a one-time pad is very simple. So what we have is a message. Here we just pretend it's a string of ones and zeros. And then we have this thing called the one-time pad. So this is the secret key that we're going to use to encrypt the message. And what we do is we just use the XOR algorithm to generate a ciphertext using that one-time pad. So basically, whenever there's two zeros between the message and the one-time pad, we put a 0. And if there's only 1 0 in one of them but not in the other, then we put a 1. And if there's two 1s, we put a 0. So that's the XOR operation. And you can prove that no matter how powerful your adversary is, if you generated a one-time pad that is truly random, no matter how much computing power they have or how smart they are, there's no way they can take the ciphertext, even if it's really, really long, and figure out anything about what the original message is. So it's essentially a perfect form of cryptography. Now, it has two big problems, though. The first big problem is that you need a really long secret key. The secret key has to be just as long as your message in order for it to work. The other problem that it has is that you somehow have to move this secret key to the other person that's going to receive your message. So there has to be some sort of separate way that you maybe meet the other party in person to give them the message, or there just has to be some way of exchanging that through a secure channel. So, and in fact, during the Cold War, there would be people with suitcases full of one-time pads that would travel between Russia and the US to do exactly this, so that the US government and the Russian government could use this type of cryptography to send messages between each other. We're going to talk about how to solve the first problem first. So the first problem is getting a smaller secret key. And then later in the talk, we're going to talk about the second problem. How do we avoid having to send this special message around? The question is there any way we can have a secret key that's shorter than our message and still have perfect security? It's easy to prove that this is not possible. In fact, because of that, one-time pads are really the only form of perfectly secure cryptography you can have. If you want a shorter secret, you have to make certain assumptions about the attacker that's trying to break into your network. And so the assumption that's commonly used is this assumption right here. So we want to create a scheme of cryptography that's secure, and we're going to say that it's secure if we have an adversary that can do calculations in probabilistic polynomial time, and if that's all they can do, they will be able to break the scheme with negligible probability. So to kind of translate this, when we as computer programmers think about how hard it is to solve certain programming problems, the important things, the most important type of problem we think about is problems that work in exponential time. So anything that requires an exponential calculation is not very efficient, and we always want to find things that are more efficient than that. So polynomial time, which is basically where let's say you have twice as big of a key for your cryptography, that would mean we would square the amount of time it takes. So that would be a polynomial time. It's actually not too bad. And so what we're saying here is our adversary can do this. They can do polynomial time, but it's not good enough to break this cryptography. So in a roundabout way, we're saying that we want to create a cryptography that requires an exponential number of calculations. The other thing we want to do is, in order to mathematically prove cryptography, what people do is they come up with mathematical descriptions of attacks that the adversary can do. And usually the way that works is that the adversary is given a random number and can run an experiment where they use that random number and try to break the cryptography. So the obvious way for an attacker to use a random number to break the cryptography is just to assume that the random number might, just by pure chance, be the secret key, and then so we try to decrypt the message with the random number, see if that works. So we want a system where that doesn't work, where it's almost impossible if you just pick a number out of a hat that it happens to be the secret key. And that's what we mean by probabilistic. So we're essentially handing the person a random number, and we want the probability that they can somehow use the random number and information about the algorithm. We want that to be negligible, that they can break the cryptography. Now, so in the classical world, the standard way of building systems that are secure, according to this definition, the most commonly used is called block ciphers. So block ciphers are pretty simple to understand. So at the basic level, what a block cipher is it's a permutation. So what we're going to do is we're going to have some numbers, and we're going to convert them into other numbers. And we're going to have a permutation like this, where we say like the 5 goes to a 0, the 2 goes to a 7, so this is called either a bijection or a permutation. And this is kind of this is a very simple way of doing cryptography. Now, in order to make this secure, there's several additional things that we're going to want to do. But this is kind of a good way of thinking about cryptography, and there's several things that we can see about this kind of idea. One is that it's very easy to undo the cryptography, right? So if I put in a 7 and I get a 5, then the person on the other end getting the message knows they can take the 5 and go backwards and get the 7. So it's easy to reverse, which is what we want. And we can also see that this is basically symmetrical. So we can see where the symmetry kind of comes from. You can go one way or the other way. But the important thing about this is that this is a very simple conceptual building block. And we can use it to build more complicated, we can use these small permutations to build more complicated permutations, which is what we're going to do next. So the things we want to do is we want to build permutations that are so complicated that we can prove that this adversary can't break the cryptography based on our definition of security. And also what we want to do is we don't want to have like these funny arrows. What we want to do is instead of these arrows, we want to have a number that basically explains the mapping between the two numbers. So if we do those two things, then we essentially have what is called a block cipher. Now here's how a block cipher is. Oh yeah. So before we talk about block ciphers, what we want to do is we want to take these simple permutations and we're going to use them to build more complicated permutations. And Claude Shannon, one of the sort of cornerstone early scientists working on information theory, came up with this idea of confusion diffusion. So the idea is that if we want to do any kind of cryptography, we want to break it into two steps. So the first step is confusion, which means making the relationship between the key and the ciphertext as complex and as involved as possible. So what this means in practice is what we're going to do is we're going to have a big piece of data that we want to encrypt, and we're going to take a little piece of that data and we're going to do something really involved with it to confuse that data. So that's sort of the confusion step. We take a small piece of our data and we confuse it. And then the next thing we want to do is diffusion. So that's where we take, it refers to the property that redundancy in the statistics of the plain text is dissipated in the statistics of the ciphertext. So what this means is instead of working just in a small area and mangling it up, what we want to do is we want to make sure that any one small piece has a large impact across other parts of our data as we're encrypting. So we kind of want to diffuse any errors across our calculation as we're encrypting something. And so these two factors together produce what is called the avalanche effect, where you can make one tiny little change in your key or in the message that you're trying to encrypt, and it will completely change the ciphertext. And that's the property that we need for secure encryption. The classical way that this is done is using something called a substitution permutation network. So this right here is a block cipher. So what we do is exactly what we said. We're going to have these little boxes that take little pieces of data from our original plain text and they mangle them up. But they can be really simple. They just mangle a small amount of data really well. And then what we want to do is we want to diffuse all the information between the different parts of the message around. So that's what those wires are. They just kind of move stuff around. And they don't worry about really encrypting it, but the point is just that we want to spread errors around. And then the last thing, instead of having keeping track of where all the little arrows are, we're just going to have our key, which kind of controls exactly how a particular block cipher is going to encode things. So this is kind of like the private key for the block cipher. We're going to just XOR, we're going to use that to XOR all the data across these levels. And so what's nice about this type of substitution permutation network is that all these steps can be reversed. So we can take our keys and we can just XOR them again to undo them. And then when we get to the diffusion part, we can just go backwards. And then those little boxes, all they do is basically swap around some numbers. We can do that. It's just a permutation. And so that way, when somebody gets our result, our message, the ciphertext, they can just, if they have the key, they can undo all of this and get back to the original message. And we can prove that it's secure, that if anyone listens, gets access to the ciphertext, that they can't crack the original message. Now the other thing to notice here also is that the plain text and the ciphertext are the same length. So the message that we put in and the length of the encoded message are the same, which will be important later on. Since the length of the plaintext and the ciphertext are always fixed, the obvious question is how are we going to encode longer messages? Because if we just work on a block, which is why it's called a block cipher, just handles a fixed number of characters, we have to figure out some way of encoding a larger message. So the obvious way to do that is we just take our message, we break it into chunks, however big the blocks are, we encode them with our block cipher, and then we get our ciphertext. If you think about that, this has some obvious problems in terms of encrypting a message, which is that if it so happens that there's some repetition in our original message, then the block cipher will do the exact same thing because it's deterministic, and we would see the same repetitions in our ciphertext, which is a bad thing. So what we have to do is come up with some system of kind of having the different parts of this encoding affect each other, and this is called cipher block chaining. So essentially we first use the block cipher to encode the first part of the message, then we take the result and we XOR it up top against the second part of the message, and then stick that into the block cipher. And this guarantees that even if there's repetitions in the message, the whole ciphertext will be completely mangled, assuming we have a good enough block cipher. So these are three encryption schemes. Again, we have private key encryption, where both the person who's creating the message and the person who is supposed to receive the message, they both have to have this private key. So these are the three most commonly used algorithms for doing this. And the first one isn't used anymore, DES, because it had a really short key. So it was actually really good, and nobody ever cracked it. But because the key is so short, you can just brute force it by trying out every key. And so there's a modification of DES called 3DES that uses a longer key and is still widely used. And then there's AES, the Advanced Encryption Standard, which is also widely used for private key encryption. Now, none of these things are actually used in cryptocurrency, as far as I know. But it turns out some of the concepts we've talked about are going to be important in the next section, which is very important to cryptocurrency, which is hashing. So hashing is the idea that we're going to have some kind of large piece of data, maybe a document, and we're going to generate a small number from that document that's like a unique fingerprint of the larger document. And you can realize all kinds of places where this would be useful. Like let's say you're building a piece of software that works like Dropbox, and two people load up a giant file, and because it's like the latest Rihanna video or whatever, everyone uploads the exact same one. Well, if you can figure out what the hash is, you can just upload it one time and know that everybody is uploading the same file. And there's lots of other places like virus detection systems use this. Things like BitTorrent rely on hashes for the files that they upload. And then we're going to get into all the various cryptocurrency applications of hashing. Now the key with hashing is that you need something called collision-resistant compression. So what we're doing is we're taking a big piece of data and we're going to compress it into something small. So that's the compression part. And then what we want to make sure is that it's collision resistant, meaning that if we have two big files that are different, even if they're just different in a tiny, tiny way, we want the number that we get as a result from our hash to always be different if possible. Now, if anybody has been watching the cryptocurrency news earlier today, there was a highly relevant story, just came out a few hours ago, about a cryptographic vulnerability in IOTA. So IOTA is one of the top 10 cryptocurrencies, I guess, according to this number 8th. I wouldn't be surprised if it's dropped based on this message. But what they found is that somebody created their own hash function called curl, and it produced collisions. So you were able to basically craft your own way of signing a transaction where you could say, I want to spend money out of this fat wallet that has $1 million in it. And because of this bug and this hash function, it would think that your signature was correct, even though you're not the owner of that wallet. And so, yeah, so this is exactly relevant to what we're talking about here. So they failed to construct a collision-resistant compression. So, how can we construct a collision-resistant compression? Well, the classical way of doing this is to use block ciphers. So in this case, what we're going to do is, as we said, a block cipher, it takes a message and it spits out a ciphertext, and both the message and the ciphertext are the same length. So you might think, well, there's no way to really compress data that way if the thing we're putting in is the same as size as the thing we're taking out. However, block ciphers, as I said, they also have a separate key. The key basically kind of controls which way all the arrows are pointing inside of the block cipher. So we can take both of those together, and then we basically can input more data that way. And then with a little trick where we XOR the key on the way out against the result, there's a way to prove if you have a high quality block cipher that essentially produces a really random result, you can prove that this will be collision resistant. And so this is a good way of just using a traditional block cipher, any block cipher, and you can create a hash function. I should correct that. There's like some obscure reasons why certain block ciphers aren't useful for this type of approach, but most block ciphers in general are. And this is called the Davies-Meyer construction. So usually what this means is we can take something that's like 200 bytes in size, and with the block cipher we can turn that into something that's only 100 bytes in size. That's essentially like a hashed version of those 200 bytes that came in. And then we can take that same idea and we can compress an even bigger file, and we do that by just chaining this sort of fixed length function over and over again. So we break our file into pieces, and as you can see, there's always two arrows going into each hash function, and it spits out one arrow. So basically, the hash function itself only compresses by a factor of 2x, but by doing this over and over again, we can compress as much as we want to, and we can again prove that this will be collision resistant. And so this is called the Merkle-Damgard transform, however that's pronounced. And with those two things together, you can use block ciphers, and you can produce a high-quality hash function. So these are the commonly used hash functions that use this type of idea. So now MD5 is not used anymore. It's been broken. People have managed to create two PDFs with different text in them that both, when you hash them with MD5, will produce the same answer. So that's like the ultimate death nail to a hashing algorithm. SHA-1 it also uses this type of approach with block ciphers, and it hasn't been broken yet, but apparently there's reason to believe that it's not going to survive much longer until somebody finds a collision. And it's even possible, I'm out of date on that somebody already has found a collision, now that I think about it. SHA-2 is like probably the most widely used one of these right now, and it's still safe at this point. And then SHA-3 is a newer type of hash function that just came out recently, like the last 5 years or something. And now it uses a slightly different algorithm than what I described. It uses something called a sponge transform, which is a little different than these transforms that we looked at. And it uses instead of using a block cipher with a key, it uses an unkeyed block cipher. So I'm not totally familiar with exactly what all these differences mean, but that one is sort of like considered to be the most modern one of these types of hashing functions. Now, unfortunately, if you read the cryptocurrency literature, things get very confusing because you see things like this. So first of all, if you ever read anything where they talk about SHA-256, that usually refers to SHA-2. So SHA-2 can have different bit sizes. One bit size that it can have is 256 bits. So if you read about the mining algorithm on Bitcoin, they'll say that it uses SHA-256. And what that really means is it uses SHA-2 with a 256-bit length. And there is also a SHA-3 256, but that's not the one they're talking about when they just talk about SHA-256. They're talking about SHA-2 256. And then what's really annoying is right after Ethereum was officially specified, the people that created SHA-3 made a minor change to the SHA-3 algorithm. So Ethereum doesn't actually use SHA-3 for its hashing. It uses a very slightly different version of SHA-3 called SHA-Kekkak. And so there's SHA-Kekkak 256 and Kekkak 512. And so those are basically SHA-3, but they're like a slightly different variant that has just a minuscule, unimportant difference. But that's the one, when people talk about SHA-3 in the Ethereum community, they're talking about this, which is actually different than SHA-3. And then when people talk about SHA, then it depends on whatever community you're in. So if you're a Bitcoin person, SHA will mean SHA-2 or SHA-256. And if you're Ethereum, it means SHA-3 because everything in Ethereum uses SHA-3. So this gets really confusing. That's kind of how these things break out. So where is hashing used in cryptocurrency? It's used in 3 different places. So the first one is it's used in proof of work. So this is these math puzzles that cryptocurrencies use to validate transactions. And so as I said, Bitcoin uses SHA-256 and Ethereum uses SHA-3. And of course they do a lot of other stuff. There's a whole algorithm called ETH-hash that Ethereum uses that has all kinds of other properties. But down at the heart of ETH-hash, if you look at the last thing it does, it uses SHA-3 or SHA-Kekkak as the algorithm. The second thing that hashing is used for is for shortening public keys in addresses. So we usually think, when we think of public key cryptography, we think that somebody who owns like a Bitcoin address or an Ethereum address, that they have a private key and a public key. But that's not really how it works. What they actually have is a private key and a public address. And there is a public key, but when you use cryptocurrency, you never use that because there's a way of converting the public key into something shorter called an address. And because it's shorter, that's the one everybody uses. And we use hashes to generate this shorter address, and I'm going to get into that a little later. The last thing we use hashing for is for organizing blockchain data. So you've probably heard that whenever we create a block, it always has the hash of the previous block. And so we use either SHA-256 for Bitcoin or SHA-Kekkak 3 for Ethereum to do that. And then the other thing is that the transactions in the block themselves use a special form of hashing that we're going to talk about next, called Merkle trees. So that's kind of the last place where hashing is used. Now, I want to cover this in greater detail because it's one of those subjects where most people that are computer programmers or interested in this stuff and they try to understand what's going on, it very quickly, their eyes kind of glaze over as they try to read through the explanation, and it's actually really cool, and it's not actually all that complicated. So it's worth spending a little time on it to understand how this works and why it's useful. So I tried to come up with a kind of a very simple example that kind of captures why Merkle trees are so cool. So right here are the 45 presidents of the United States. So I just got this off of the internet, and I put that into a file called presidents.txt. Then on my Unix machine, I just list out the file, and I can see that file is 839 bytes in size. And now let's decide that's too big for me. I would like to have it compressed. And so what I'm going to do is I'm going to use the tar utility, and we're going to zip it down, and let's see how big it gets when we do that. Well, it gets down to 637 bytes. So it's like something like a 25% decrease. And if this was a larger file with more text in it, it might get up to 50 or 60% or something like that compression. So this is usually what we think of when we think of compression. You might get like a factor of 2 improvement in compression. So now what we can do is we can actually use this thing called a Merkle tree to compress our file of presidents. And if we do that, we get this thing called the Merkle root, which is essentially a compressed version of this database of presidents. And it's only 32 bytes in size. So that's like a 95% compression of our files of presidents. And if you know anything about compression, like that sounds like it's too good to be true. There has to be a catch. How can we compress it 95%? And yeah, there is a big catch. And the catch is that after you compress this list of presidents, you no longer have any way to decompress the list of presidents. So then the question is, how can this be useful? If you can't decompress it, what good is compression? And that's what we're going to talk about next. So first of all, let me talk about how we create what a Merkle tree is and how we're going to compress our data. And it's very simple. What we're going to do is we're going to take the presidents, and I did this on my computer yesterday. I built this Merkle tree out of these presidents. And so here's two presidents, William McKinley and Grover Cleveland. And we just take the SHA of those two presidents, and it gives you a long 32-byte number here. Here I have it abbreviated. So those are the SHAs of those two names. And then what we do is we just concatenate those two SHAs together, and we do another SHA. And so you see the number that begins with 413A. So that's basically a SHA of SHAs, where we're compressing the names, and then we're taking those together and compressing them again. And we're just going to keep doing this. And so we build a tree out of all the presidents. So there's other presidents over here and over there. And I'm just showing you one path, starting with Grover Cleveland all the way to the top. And if we compress all the presidents together this way, we end up with the Merkle root, which was that thing I showed you before that begins with D0F up top there. Now what's interesting about this is that if we look at it this way, you can see there's a path from Grover Cleveland all the way up to the top. And you can calculate how long this path would be. It would be the log base 2 of however many files there are. So if you have, let's say, 1,000 people in your database, it might be a path of 10 or 11 to go down, or actually it would be 9 or 10 to go down. So that means that the path is actually relatively short if you have lots and lots of people. And at each branch, there's a number which represents all the other people that kind of got hashed in at that branch. And so in this case with Grover Cleveland, there's 6 of these spots where basically external data is coming into our tree here. And so we can take those blue boxes there, and we can put these in a list, and this is called a Merkle proof. And what's cool about this is that if I have this Merkle root, somebody can come to me and say, hey, did you know Grover Cleveland was once a president? And I'm like, oh no, I don't believe that. And then they can say, no, I can prove it to you. You know what the Merkle root is. And here are these 6 boxes with the Merkle proof that have all the other presidents in them. And using that, you can fill in these empty boxes that I have there by just hashing together those numbers. And you can come up with that result. And so that way, without having the list of presidents, only having those 32 bytes, you can prove to somebody that any one person is actually a president. So in some way, we are capturing the entire data and making it accessible to the recipient. And so the place where this kind of concept is valuable is in 2 places. Number one is on resource-constrained hardware. So if you download a Bitcoin wallet for your phone, usually that is something called a light wallet or an SPV wallet. And so it doesn't hold the entire blockchain because it would take up too much space on your phone. Instead, it only holds the headers for the blocks. But people can still prove to you that a transaction is in a block by using this Merkle proof. So basically what we're doing is we're trading storage, because the phone can't store very much, by forcing the phone to do more calculations, to do these SHA calculations, and we can actually prove the existence of a much, much, much larger amount of data. The other place where this is useful is if you're doing smart contract programming like in Ethereum, because if you want to store a piece of data in a smart contract in Ethereum, it's many orders of magnitude more expensive than to do a calculation. I don't know exactly what the ratio is, but it's probably like if you want to do a SHA in a smart contract versus storing just a value in a smart contract, it's probably like 1,000 to 1 cost difference in terms of the fee you have to pay on the Ethereum network. So here we can essentially just do a few more SHAs and we don't have to store the entire database. And so that's a really good payoff for smart contracts. And so if you want to store large amounts of data on a smart contract, in a smart contract, I recommend you learn about Merkle trees. Now, so now we've talked about classical techniques. So this is all stuff that uses very straightforward math, and there's proofs in terms of security and stuff. But around the 1970s, things kind of get crazy. And this is where people started playing around with this concept called public key cryptography. And so the idea here is that instead of you and the recipient of the message needing to share the same private secret, what you're going to do is everybody's just going to publish a public key, and they're going to keep a private key to themselves. And then if you want to send a message to somebody, as long as you know their public key, you can encrypt the message using their public key and send them the message. And even if there's eavesdroppers that capture the encrypted message, they can't decode it. And so this is a completely new, more powerful way of doing cryptography. Now, it's actually really hard to figure out exactly who invented public key cryptography. And so these are sort of like the contenders. And so the very first people to work with this stuff were in the 1970 to 73 range. And these are people who work for British intelligence, a little typo there, for the computer encryption security group or something like that. And so these people invented these concepts. So James Ellis was the first. He came up with the idea, and then Clifford Koch in 1973 had the first working implementation of this. But we only know that retrospectively because these things were declassified. Similarly, there is talk that the NSA also around the same time had come up with this concept, but there's not as much good documentation around that, so it's not known if that's really true. In terms of public algorithms, the first people to kind of have an influence in this area are Whitfield Diffie and Martin Hellman. So they published a paper called New Directions in Cryptography, and they did two things. One is they just pointed out this concept that there are certain types of math functions that are easy to do in one direction and hard to do in the other direction, called one-way functions. And you might be able to use those to do really interesting cryptography. And the other thing they came up with is a more limited form of public key cryptography called the Diffie-Hellman key exchange algorithm. So that wasn't really true general purpose public key cryptography, but it was close. And then a year later is when the people whose names begin with RS and A came up with the RSA algorithm. So that was the first true public key algorithm that was described. But then to confuse things, in 1985, this guy named Taher Al-Gamal came up with Al-Gamal encryption. And all Al-Gamal encryption is that he read the original paper from Diffie-Hellman in 1976 and said, oh, you know what, these guys actually did have general purpose public key cryptography described in their paper, but they didn't realize it. And so it gets confusing. But anyway, these are kind of the people that came up with this idea. Now, in order to talk about this, we have to get into number theory and like weird math. I'm just going to touch on this a little bit. So as I said, the goal here is that we want to do some kind of deterministic calculation where it's easy to do it one way, but it's not easy to do it the other way, so it's asymmetric. So when we go forward, we want to be able to compute it in polynomial time, which, as I described, means that you can do it quickly. But then the inverse, we don't want to be able to do in polynomial time. And if we could come up with a function that would work that way, then we could build new forms of cryptography. And so what are the candidates for how you could do that? So the most obvious thing that people will think of is prime factoring. So it's very easy to find large primes. And it's very easy, if you have two large primes, to multiply them together to make an even larger number. But then it's very, very, very hard to figure out what the original two primes were when you have that final number, even though in theory you have all the information you need to solve that problem. But it turns out that there's really no way to use prime factoring itself to do any kind of cryptography. You need some more ideas. So the main sort of new ideas that everybody has used since then is this concept of cyclic groups. And there's sort of two main types of cyclic groups that are used. One is modular arithmetic, and the other one is elliptic curves. So a cyclic group is pretty simple. All it means is we have a set, a group, and we start off with one value in that set, and then we have some kind of generator function that we can run over and over again against the number in the group to create more numbers. So that's all a cyclic group is. And some types of cyclic groups turn out to be really useful for creating one-way functions. So the first one involves modular arithmetic. And modular arithmetic, what that basically means is we're going to come up with a math using positive integers. And when we multiply those numbers or we add those numbers, we just always run modulus by some number, in this case 137. So essentially, if it's bigger than 137, we only take the remainder less than 137. And so it turns out, so you can kind of imagine, as we generate things and we do arithmetic with this type of modular arithmetic, we're just always constantly going to hit we're going to go over 137 all the time, and it's going to kind of cycle back, and you can kind of see it's kind of like mixing an egg to make scrambled eggs, and it makes it very hard to unscramble the eggs. And what's important is that you can have math problems like this, like 5 to the 57th power, and then we take a modulus by some number. So if you try to figure out how to calculate something like that, it's actually tricky. But there's this thing called the Chinese remainder theorem, which if you use that, makes it very easy to solve those types of math problems. So that means when we take 5 to the 57th power mod 137, we can calculate that very quickly. But if I give you the result of what that answer is and ask you, I multiplied something by something else, or I multiplied 5 by some exponent, can you tell me what that is, what the exponent was? It's a much more difficult problem to figure that out, to go backwards. And so we can use that to create a one-way function. And then the other way, which is very similar, is to use elliptic curves. And so basically what we do here is we scramble things in a different way. So there's this concept called an elliptic curve, and we can take points that are on that curve and we can multiply them or add them. And with elliptic curves, multiplying them and add them has special meanings. In the case of adding them, what that means is that we're going to take, if we have a point here and a point there, we draw a line and it's going to hit another point, and we're going to say that means we added those two numbers. And it turns out that in the same way, we can kind of scramble an egg this way, because we're going to keep bouncing between different numbers on this curve by using that kind of technique. And then it's very hard later on to figure out how to undo that. And that's also a good way to do this type of cryptography. So the difference with elliptic curves is that it's a much harder cryptography to break, but we have less math to prove that it's correct. So that's kind of the trade-off. Do you want something that's fast and has small keys then you use elliptic curves. If you want something that has more history behind it and is more proven, then you use modular arithmetic. So, so now let's get into public key cryptography, which uses this concept. And I should mention, again, public key cryptography is not really something that's used in cryptocurrency. You don't use Bitcoin to send secret messages between people. So we're going to use all these ideas from public key cryptography, but in cryptocurrency, we're going to use it for something else. We're going to use it for digital signatures, which is very closely related to this. In order to, I figured it would be useful. It's kind of hard to get to really cover public key cryptography quickly. So I figure what would be more interesting is if we go over a specific example and do some actual math and see kind of what it looks like, and maybe you can kind of get a flavor for how this works. So this right here is the algorithm for El-Gamal encryption. And as I said earlier, so the people, the Diffie-Hellman people, this is essentially the idea in their paper applied to create public key cryptography. And we're going to kind of go through this in detail in the next slides. But the basic idea is up here we basically come up with a system of numbers, and then we use that system of numbers to create a generator that generates a public and private key. Next, we create a function that can encode a message, and then last we're going to create a function that decodes a message. And we're going to use this concept of modular arithmetic to do that. So let's do the first step. So just what it says here is let G be a polynomial time algorithm that on input 1n outputs a cyclic group G. Its order Q, where Q, the count in Q is n, and a generator G. So it doesn't really mean that much. What it basically means is we just want to generate a set of numbers that we're going to start with for our cryptography. In this case, we can kind of pick something. So I'm going to say we're going to have a total of 83 numbers that we're going to work with. That's going to be our Q. And then we, in order to do this thing with the generator, we need a bigger number that says kind of what the integers are we're going to work with. So we're going to work with the first 167 integers, which is this P, but we're only going to use 83 of those for our math problem, because we're only going to use the ones that are squares modulo P. So basically the perfect squares in those numbers, but with a modulo P difference. And then we need another number, which is a generator. And so basically, as I said, a cyclic group, we take a number and we apply a generator over and over again to generate more numbers. In this case, G is 4. So what we're going to do is we're going to take a number and we're going to generate a new number by multiplying it by 4. And so now we have basically described a system of numbers, a cyclic group that we can use to do public key cryptography. So now we want to generate keys with this. So we want to generate a private key and a public key. So the first thing we have to do is we have to choose a random x, which it goes up to q. So it has to be a number from 1 to 83, because 83 was our q. And so we're going to pick 37 as the secret key. So this is basically our secret key. Of course, we're using a really small number in this example. It would have to be a very, very large number to be secure. Then, using that number, we can create a private key. And it says exactly here how to do that. We just tell it how many total numbers there are, 167. And then Q, how many of those are we using? We're using 83. Our generator that we're using to generate numbers, so we're multiplying by 4, that's 4. And then our secret is 37. And so that is our private key. And then we come up with this thing called H, which is where we take our generator and multiply it and put it to the xth power. And that's 4 to the 37th mod 167. We also have to do everything mod 167, because that's what our modular loop is when we're scrambling our eggs. And that gives us H, and that gives us our public key, which is there. So now we have a private key and a public key. Next, we need a message. So we have a message, and the message has to be one of the numbers up to our P, and we'll pick the number 65 as our secret message. Then we just choose any random number up to 83, so we picked 71. And using this, we can now do this simple math problem down here, and come up with an encrypted version of the message, which is this 132.44. And you just follow the instructions there. It's pretty straightforward. And now, after we've done that, we can decode the message. So in this case, we just follow the instructions. We use the secret key. So because I'm now decoding it, I have the secret key. I'm the person who can decode these messages. And we take the two parts of the ciphertext. We do this little piece of math, and we get 65. And so with this type of design, you can have a public key that you can publicly show to anybody in the world, and people can use that to encrypt messages, send them to you, and you're the only person in the world that can decode that message. But of course, we'd have to use a much larger cyclic group in order for this to be secure. But this is the basic concept. And here we're using modular arithmetic. As I said well, I haven't said this yet, but in both Ethereum and Bitcoin, they use the elliptic curve cryptography, which follows the exact same principle, but is a little more complicated because it uses it builds cyclic groups out of elliptic curves instead of modular arithmetic. Now, so now we get to digital signatures. So as I said, we don't really use public cryptography directly, but we do use digital signatures. Now, one thing that is kind of confusing whenever you read about digital signatures and you don't know about any of the cryptography is you'll always see these numbers called R, S, and V. So I just kind of want to describe where all of this comes from and what it means. When you do public cryptography, it's an interactive protocol. You want to send a message to someone, and there's kind of things that you send back and forth to each other to do this. The same thing happens when we try to use public keys in order to identify ourselves. So you can use public key cryptography to come up with what is called an identification scheme. And an identification scheme is basically the same as a signature, like in Bitcoin or Ethereum, except that it's interactive. So we actually have to talk with another person to prove to them that we signed the transaction, basically. So what happens is that the prover can use their private key to generate this random number called I. So it's not random. It's you pick it out of a sampling based on your private key, and you send that to the verifier. And then the verifier uses the public key, and it generates it samples a number based on an algorithm that's again sort of semi-random called R, and they send that to the prover. And then the prover can send after that calculating using I and some other information they calculate at the same time as I, and using R, they can calculate this thing called S. And that S goes back to the verifier, and then the verifier can use that to validate that the prover has some kind of private key for which the verifier has a public key. So this is kind of the same idea as with the cryptography, but what we're trying to do here is just identify ourselves. Like I say to you, hey, I'm Bob, and Bob's public key is this, and I can prove to you that I have the private key. And we have to do this little dance of sending these numbers around in order to prove that. Now this isn't useful for what you want to do with Bitcoin or Ethereum, because what we want to do there is we want a non-interactive protocol where essentially you create a message to purchase a cup of coffee using Bitcoin, and you want to sign that transaction that gives the coffee shop your Bitcoin, and you don't want to have a conversation with them. You just want to sign the transaction and just attach it to the data, and then anybody who gets the transaction can see that you've verified, you've proven that you're the owner of the account where that money came from. So there's different ways of converting these identification schemes, these interactive identification schemes, into non-interactive signatures. So the main one that's used is called the Fiat-Shamir transform, and it's basically just an algorithm for taking this and converting it into something non-interactive. So we can use that to get what we really want, which is a thing where we take a transaction. In this case a transaction hash. And we know, I know, you know, so the coffee shop knows what your public key is, well, the coffee shop doesn't, but the wallet owned by the coffee shop, the Bitcoin or Ethereum wallet owned by the coffee shop, knows that supposedly money from this certain public key has gotten into the coffee shop wallet, and we want to make sure that the person who owns that public key where the money came from signed the transaction, and that they have enough money to pay for the transaction in their account. And so we take the public key where the money came from, and then we use the two numbers R and S, just like with that interactive scheme. And these two together make up the signature that proves that the hash was signed by the public key. So this is the signature, this is the key that signed it, this is the thing that was signed, and so you can create a function called EC-verify that returns true or false. Yes, this person used that signature to sign that transaction. Now, I should point out, why are we using a transaction hash? Why don't we just use the whole transaction to validate it? And the answer is that public key cryptography is a lot more computationally intensive than private key cryptography. And so, and since hash is built on private key cryptography, we can take a long transaction, we can compress it down to 32 bytes, and we can get the same benefits from signing with the public key, but we can have a smaller piece of data. So you use both. You use the private key cryptography, the block cipher, to sign to hash down the number to something small, and then you use public key cryptography to sign it. Yeah, so this is what you could do, but if you look at any library that in either Bitcoin or Ethereum that uses elliptic curves to sign transactions, this is actually the function signature you have. You don't have a public key in there, and then you have this thing called V. And the reason for that is that it turns out, you know, the signature is actually pretty big. And it turns out that if you have the hash of the thing that you're signing, and you have the signature, you have almost all the information you need to figure out what the public key is. And the thing with public keys is, as I said, nobody uses them because they're really, really long. Everyone uses addresses. So wouldn't it be great if you could just check a transaction and figure out what the public key is? Because if you could do that, you wouldn't actually have to identify people by their public key, because then you can take the long public key and you can compress that down again with a hash into something shorter. And then that's what you use to identify people. So what Bitcoin and Ethereum uses, they have a function called EC-recover, which actually outputs the public key. So you can essentially create public keys on demand, and then you can just shrink this down into something tiny. And that way everybody who has Bitcoin or Ethereum stored on the blockchain, they only need a really short address to identify them. They don't need the whole long public key, because you can always figure out what their public key is every time you verify a transaction. The problem is that it turns out you can't totally get rid of the public key, because there's like a little piece of data, which is I think like 2 or 3 bits that are not recoverable. So you can't just from R and S and the hash, you can't figure out what the public key is. So they come up with this thing called V, which is just a byte long. It's a short number. It's usually something like 27 or 28. It's always like the same 3 or 4 different numbers. And if you have that, you can with EC recover, you can actually return the private key. So it's a much more efficient way of, because you can generate public keys on demand, you don't have to store those on the blockchain. And so if you want to know how addresses are, public addresses are really encoded in Bitcoin and Ethereum, these are the actual algorithms. So in Bitcoin, we take the public key encoded with the elliptic curve DSA algorithm that we talked about. Then we take the SHA-256, which again is a version of SHA-2. And then the funny thing is that SHA-256 was developed by the NIST, a US government agency, or they ran a contest and selected that one. And so the Bitcoin creator decided that he doesn't necessarily trust the US government. So it turns out there's a different hashing algorithm called RIPE-MD, which was created by the EU. So what this person did is they hash by both of those algorithms, hoping that if either the US or the EU are like creating hashes with backdoors, that if we use both of them together, they're probably not both colluding. So then we can get a valid hash. And then the last thing Bitcoin does is it does this thing with a checksum where it encodes it in a special way. And what this means is that if you type in manually somebody's Bitcoin address on your phone and you have a typo and you try to send money to that typo address, it won't go through. It'll give you an error saying this isn't a valid address. Now, Ethereum doesn't do that. And so if you read early on when Ethereum first launched, there were lots of people basically mistyping addresses and basically sending all their money into a black hole where it couldn't be recovered, and that was kind of embarrassing. Since then, they've come up with kind of a halfway solution that I won't get into that addresses most of that. But in Ethereum, all we do is we take the public key, and then instead of the SHA-256, we use the SHA-3 Keccak algorithm, and then we just take the rightmost 160 bits, and we call that your Ethereum address. So those are the two algorithms that are used for addresses. And this means we never have to store public keys on the blockchain because they're long and unwieldy. We just store these shorter addresses, but we can always generate public keys on demand using the transactions. Now, so we talked about the two types of math, and then as Vitalik likes to say, there's a third type of math that's coming out now called moon math, which I barely understand, but I'll just try to give a basic flavor of what's going on here. So this is this thing where you hear about zero knowledge proofs, and I'm just going to kind of try to describe what this is about. So this is the next generation. The generic term for this is homomorphic encryption. And conceptually, what we want to do is this. It's pretty simple. This is our dream. What we want to do is we want to take a computer program and we want to encrypt it, and then we want to take a bunch of data that we want to feed into our computer program, and we're going to encrypt that too. And then we send both of these things to somebody else's computer, and because they're both encrypted, that person can't figure out what you're doing, what the program does, or what the data is. And then we're going to run something on that computer, and then it's going to spit out an encrypted output data and give it back to us. And then we know somehow how to decrypt that data. And so this is the dream here is essentially that you can run secret algorithms on other people's computers, and they don't know what's happening, but you can get their results back and decrypt them. So if you can do this, there's all kinds of neat computer sciencey things you can do if you solve this problem. And people have now figured out how to do this in certain limited ways and found useful applications for this. Now it's really hard to even come to grips with the math behind this. So this is kind of my analogy that I like to use personally when I think about these types of homomorphic encryption problems. And so your mileage may vary with this analogy. It might be that if I study this stuff for another 6 months, I'll realize this is a horrible way to mislead you about how to explain this stuff. But here's my best attempt to kind of give you an understanding of how to think about this. So let's say somebody proposed that problem to you, running these encrypted programs on other people's computers, and you wanted to just, you don't know anything about advanced cryptography, and you want to come up with a way that you might be able to do this. Like, how might you do it? So, and this is kind of what I might think about doing. So the first thing I would do is I would take a bunch of random noise, just basically a giant matrix of random numbers. And then what I'm going to do is the input data for the problem that I'm trying to solve, I'm just going to tweak a few of those numbers in that big chunk of random data. And anyone looking at that, it would still look like random data to them because they don't know, what numbers are being tweaked or to what amount. So now this isn't really what's happening. What's happening in real homomorphic encryption is a far more advanced type of tweaking here. But this is just to give you kind of a rough idea of what's happening. And then what we do is on the person's computer that's going to run this, we run some kind of long, tedious calculation that has lots and lots of busy work. So basically, we hand them this giant chunk of data, and somewhere in there, a needle in a haystack is our actual problem that we're trying to solve. And then they run this really long and tedious calculation and give us the result. And so, and because it's such a long, tedious calculation, they can't figure out at what point they actually solved the problem that we wanted them to solve. But we know that these three numbers here are going to be tweaked in just the right way to give us our answer back. And so this is kind of how you can think about it. And if you think of this type of design, two things are apparent. The first thing is that you're going to need like really, really big chunks of data, and you're going to have to run really, really long calculations. And that's exactly what you find. If you look at these people working on these homomorphic encryptions, you'll hear like news stories about how they ran their computer for like a month or whatever to add 2 numbers or something like that. And and they keep getting better. Now they can do it much faster. But it involves these tedious calculations and this large amounts of data. And the other thing that's obvious looking at this is that the way I described it here, we don't really have any way of influencing what the calculation is. So I said our goal was that we would encrypt the computer program too. So how can we use this idea to run a program, right? And the answer is that we have to figure out how to take a computer program and turn it into a bunch of numbers. And that's basically what you do when you build homomorphic encryption. And so the basic structure of this, and this is if you look up Vitalik Buterin, and he has a bunch of posts that are much more useful than what I'm describing here. This is just really touching on the subject where he goes over all these things. But the basic idea is you take your computer program and you kind of simplify it into a very simple computer program called an algebraic circuit. So an algebraic circuit, it's kind of like an assembly language, a mathematic-y assembly language. And then you'd go another step and you create an R1CS, an R1 constraint system. And this is almost like you're creating a microchip with like bare wires. It's a super, super primitive way of mathematically describing a computer program. And then you take that and you turn it into a quadratic, I forget what the A stands for now, but it's a polynomial equation that is an encoding of the constraints that describe the calculation that you're running. And so you can kind of see how that fits into the earlier picture I showed you. Because if you know about systems of linear equations, what do you have? You have a big matrix of numbers. And so what we're doing essentially is, you have this big matrix of numbers, which basically describes like a squiggly line that's like, that has 100 dimensions or whatever. And somewhere inside that squiggly line represented by all those numbers, we're encoding some math problem that we're trying to solve. And we send that over to the computer. So we're kind of turning our algorithm into like these raw numbers and hiding it behind a bunch of noise in a way. Anyway, that's kind of how I like to think about it. Now, as I said, the big problem here is that we have to deal with large amounts of data. So one of the big innovations with homomorphic encryption recently was this concept of a ZK snark. And just by the name, we can kind of have an idea of what it is. So first of all, it's succinct, which is what we want, right? We don't want to, instead of having really, really big matrices, we want smaller ones. And so this kind of helps us make things smaller and more manageable. It's non-interactive. So that's exactly what I was talking about with the elliptic curve signatures. We don't want to have to interact with people. We want to just have a transaction. We want to sign it. And people don't have to interact with us to be able to know that we are the person who signed that. So that's useful for us. And then we want to display some kind of knowledge. In this case, if you're dealing with a currency, the knowledge that you would want to show somebody is that your account has at least the $5 that you're using to pay for a cup of coffee. So you want to prove that yes, your account has $5, and since you're sending the money from your account, that therefore the cup of coffee was paid for. And we want this to be zero knowledge, meaning that just because somebody gets a transaction for the $5, we don't want them to know how much money in total is in our bank account. So So that's the zero knowledge part. And so this kind of idea, which is sort of a subset of homomorphic encryption, is what's used for Zcash, which is essentially the most advanced cryptographic currency right now. And it allows for essentially complete unanimity for moving currencies between people. And you can't figure out how much money someone has when they send you money. And if you just look at the blockchain in Zcash, you can't figure out how the money moving around links together with other money that's moving around. Additionally, the next version of Ethereum is going to have primitives for addition and scalar multiplication on some elliptic curve, and I have no idea what this means, but supposedly this means we can do the same thing. So we'll be able to have, in the next version of Ethereum, which is Metropolis, you'll be able to do secret transactions of money between people and do other cool things. Now I should mention that Ethereum Metropolis, there was going to be one release, and just recently they decided that some parts of what they wanted to put into Metropolis are close to done, and those are going to be released sometime later this month, I think. So that'll be the first release of Metropolis, and I don't think the second release of Metropolis, where they're going to put in the zero knowledge stuff, is it hasn't been announced when that's coming yet. So that'll be probably October or November or something like that. So it's still a little bit down the road, but not too far. Yeah, so that's basically how that works. And yeah, that was my talk on cryptocurrency and cryptography and cryptocurrency.